Right, ladies and gentlemen, welcome back to Manufacturing and Design MOW 217. Today we're going to start off with a new study theme called Fenner Chain Drives. So this is not one of the Shigley chapters that we're going to cover. Instead, we're going to make use of catalogs to do our selection for these chain drive mechanisms. Right, so to jump in, perhaps just to give you a bit of an overview of Fenner. So they are a power transmissions company and a very well-known name when it comes to power transmission systems. So in addition to the chain drives that we're going to consider today, they actually have quite a few different products that one can use for transmission. So one of them being the transmission belts. I think most of you would probably know this from vehicles having fan belts and cam belts, where you have some sort of a grooved belt that then connects to different parallel shafts, and power is then transmitted from one of the shafts to the other. Then, of course, chain drives, which works on more or less the same principle. However, instead of having these discs with these grooves and then also these belts with the grooves, we instead have sprockets with teeth that then interface with these chain links to transmit the power between two parallel shafts. So in addition to these parallel shaft transmission systems, we also have something known as a coupling. So a coupling is then used to transmit power from an input shaft to an output shaft, with both the shafts being coaxial, so lying on the same central axis. Gearboxes are also then provided by Fenner and any gearbox components that you would require. Once again, one of the more common applications would be within vehicles, where you have these complex sets of gears that are then placed inside the gearboxes. These gears then allow you to achieve different gear ratios, which then translates to different rotational speeds and power outputs as well as you are driving the vehicle. In addition to this, we also have inverters and then also shaft fixings that Fenner also provides. So for the shaft fixings, we're going to look at this a bit later on when we actually do or when we want to find the product code pertaining to certain taper lock bushes that we want to use on the sprocket systems for our chain drives. Okay, so with that being said, just to give you a bit of background with regards to the chain drives. So roller chain technology has evolved over the centuries. During this time, new design features and production processes have also been introduced. The new Fenner roller chain products are a result of this technology. So the products that Fenner then offers are British, German, and American power transmission roller chains. We also have stainless steel and lube-free variants for these chain sprocket systems. All Fenner chains can also be supplied to the specific lengths depending on the design that you are looking at and the requirements for your specific design. And a comprehensive range of Fenner taper lock sprockets plus any pilot bore sprockets and plate wheels are also available in their catalogs. Okay, so now to jump into the actual design spreadsheets or the design data that we're going to require for our design of these chain sprockets. You'll see we have this table over here. This is also then given in this Fenner chain drives catalog over here. So perhaps if I go to the chain drives catalog, you will see on page 1, you also have the design data required table over here. And this basically pertains to the information that you're going to require to design your actual chain drive. So some of the points that we will need would be the type of prime mover or driving machine, the electric motor starting arrangement as well, and then we also need the rotational speed of the driving machine as well as the driven machine so that we can determine the speed ratio and use that. And then we also have the power rating of the driven or the driving machine, the type of driven machine we also need, and then the hours per day of duty or the frequency of use of this chain drive mechanism will also be required. And then both the driven and the driving machine shaft diameters. And this will allow us to, at the end, formulate our actual chain drive specification. If we have any space constraints, we also need to take that into account. So this might influence the distance between the centers. And then if we have lubrication in our system. So what are the speeds that we are actually rotating these shafts at? Would lubrication be required for these systems? And then, of course, any environmental issues as well. So what is the effect of the ambient temperature? Are there any noise limits that we need to take into account? And are there any fluids that the chain drive might interact with that might hinder its motion or its performance? So something like water, oil, mist, solvents, the type of lubrication that we use, all those kind of things. Okay, so once we have the design data available, then we can move on to the selection steps, and these steps are also then given in the catalog. So if I quickly go back to page 3, you'll see over here we also have the selection steps. So just to make it a bit easier, I'm instead going back to the slides, and I'm just going to work through the descriptions over here. So firstly, we need to go and determine the service factor, and this is determined from table 1 on page 3. So on the catalog, you'll see it's this table over here. And the service factor is then determined based on a few different things. So firstly, the type of driven machine, or the type of driving machine that we have, or the prime mover. So we can either have a soft or a heavy start, and depending on the application that we're looking at, our mechanism will fall under one of these two categories. So once we've determined what the category over there is, then we know in which section over here we're going to work. Then we also need to determine the type of driven machine that we have. So we can either have a light, a medium, or a heavy duty. So in the case, let's say, for example, say we have light duty, then we limit ourselves to the row that we're going to select the service factor from. And then finally, we also need the hours per day of duty that we need. So in this case, I will need to select it from one of these three values, depending on whether I have 10 or under hours per day duty. Between 10 and 16 hours, I would select this value over here. Otherwise, more than 16 hours would be the 1.3 value, for example. Okay, so if we have the type of driving machine, the type of driven machine, and the hours per day of duty available, then we can go and select our service factor. Right, then it's a matter of calculating the design power, and this is partially done with the information that is provided. So we're going to use the normal running power which is provided and simply multiply this by the service factor from step A. So this then gives us the design power, which is used as the basis for selecting the drive and also determining the chain pitch for step C. Okay, so in step C, to determine this chain pitch, we're going to table 2 on page 4. And we trace to the right along the horizontal axis to the RPM of the faster shaft. So you'll remember that we give the RPM of both the faster and the slowest shaft. You're going to use the faster shaft RPM for that. And then you simply trace upwards to the design power to determine the chain pitch that you're going to work with. So just to show you this, if we head back to the catalog, you'll see on page 4 you have table 2. So once I have the RPM available, I have the design power available, then I can go and trace this on the graph, and I can determine in which region I'm going to lie over here to determine the chain pitch. So you'll see with regards to the chain pitch, firstly we have this code over here, which denotes the chain pitch designation, whereafter we then have the chain of the pitch of the chain in inches, and then in brackets we will have the chain of the pitch in millimeters. Right, so once I'm done with step C, I'll then move over to the speed ratio, and the speed ratio will always be the speed of the fastest shaft divided by the speed of the slowest shaft, and that is then simply determined from the design data that we give you. So you'll have the rotational speed for both shafts available. And then it's just a matter of going and selecting your sprocket sizes. So this we do in table 4 or page 6. And we select the driving and the driven sprockets to match the speed ratio found in step D. So if we look at page 6 over here, you'll notice in table 4 that we then have all of the speed ratios given here in the middle. And then on the side we have the number of teeth on our sprockets that we can go and select. So if we don't have any space constraints, we can actually use the ratios in bold, and you'll see here we have a footnote as well that says that the ratios in bold type can generally be achieved using Fenner taper-lock sprockets. Okay, so if we don't have any space constraints, to play it safe, we can rather use one of the bolded speed ratios. Once we have the speed ratio available, we can read upward to find the number of teeth on one of our sprockets, and then leftward to find the number of teeth on one of the other sprockets. Okay, so with that then done, we can move over to step F, and this is simply to calculate the power rating, or to find the power rating from our power rating tables. So these tables are given on page 5, and we then need the pitch of the chain that we determined in step C for this. So we read down the left-hand column to the rotational speed of the faster shaft. On this line, we read the power rating for the simplex chain selected. These tables are then for 19-tooth sprockets. So if a sprocket with a different number of teeth is used, we will actually need to go and apply the sprocket factor, which is also at the bottom of page 5. If the power rating figure does not equal or preferably exceed the design power calculated in step B, then we can either select a larger pitch, so we go back to step C and select a larger pitch, or we need to use a multiple strand chain. So you'll see in the table as well, you have either a simplex, a duplex, or a triplex chain to choose from. Ideally, we want to start with a simplex strand or a single strand chain, since it offers the most economical or the most financially feasible solution. And should we then find that design or that power rating is then lower than the design power, then we can start stepping up to a duplex or a triplex. Okay, so just to show you this in the table as well, so if I go back to page 5, if we, for example, work with a 16B chain, then you can go and select the RPM. Once you have that available, you'll see for 19 teeth, I have a simplex, duplex, and a triplex power rating. So if I start off with a simplex chain rating, I see that the power rating is greater than the design power, then I can select that one and it should be sufficient. Okay, so then moving on to the last step, which is then the chain length. We do have a formula available to go and calculate that. So the chain length calculation is simply L equal to 2C over P plus T divided by 2 plus KP over C. So in that case, what we would be doing is first determining what the recommended center distance is. So this we will find from, I think, page 2, if I'm not mistaken, page 2 or 3. Then we also have the pitch of the chain in millimeters. And then we have the number of teeth on the larger sprocket and the smaller sprocket. So these are respectively shown as a capital T and a small letter t. And then finally, we also want to go and determine the K factor over here. So this is given in table 3 as well, just above the speed ratios table. Okay, so and then L we just need to take note of is your length of the chain in pitches. So if I perhaps want to convert this from pitches to millimeters, then I can simply take L and multiply it by P. And that will then give me the length of the chain in millimeters. Okay, so the calculated number of pitches should be rounded up to an even whole number of pitches. If the center distance cannot be adjusted to allow for the use of an even number of pitches, it may be necessary to use an offset or a cranked link, in which case the chain power rating will need to be reduced. And you can also consult your authorized distributor with regards to options that are available for these offset or cranked links that you have available. Okay, so then we also just want to recalculate the exact center distance. So for this, we will be using the goal seek function. However, as a first estimate, we can actually use the recommended center distance that we will obtain from the tables to perform our calculation of this chain length over here. If a jockey or a tensioning sprocket is then used, we add an extra 2 pitches. To obtain the chain length in millimeters, we simply multiply the number of pitches by the pitch of the chain, like we said earlier. Okay, so to perhaps illustrate all of these selection steps, let's do it at the hand of an example. So over here we have example 1. And this example then says we need to select a chain to transmit 1.5 kilowatt of power from a gearbox running at 80 RPM. So we know that our gearbox is then the driving shaft or the driving system. And over here they give us the 80 RPM, so that is the RPM of the driving machine. So then it also says it is driven by a direct online electric motor, and we want to transmit this power to a uniformly loaded conveyor drive shaft, which is required to run at approximately 40 RPM for 12 hours per day duty. Okay, so the very first step is then to go and calculate the service factor. So we're going back to page 3 for that. Alright, so what they told us over there is we're working with a direct online start motor. So in that case, if we look at the heavy starts application, we can see that for AC we have this direct online start over here. So that means whenever we select our service factor, we want to stay in this selected block over here. Once that is done, we can also look at the driven machine. So we said it's a uniformly loaded conveyor. If we look at light duty, we can see that for belt conveyors that are uniformly loaded, they actually fall under this light duty case. So we're just going to work in this row over here. So in other words, whatever value we're going to select for our service factor needs to be one of these 3 values. And to finally determine that value, we will use the hours per day of duty. And since we're working with 12 hours per day, we're between 10 and 16 hours. In other words, our service factor needs to be this 1.2 millimeters as well. Or 1.2, sorry, there's no unit associated with the service factor. Since it's simply a service factor, we don't assign any unit to it. So 1.2 is the value that we get for the first step. Okay, so then the next step is determining the design power. So we want to then multiply the normal running power by the actual service factor. So our normal running power was given as 1.5 kilowatt. We now know that our service factor is 1.2. So all I have to say is 1.5 kilowatt times 1.2. So the value that I'm going to get out is this 1.8 kilowatt design power over here. Right, so once that is done, we can then move over to the chain pitch. And for this, we need to use table 2 or the figure that we have over here on page 4 to go and select the region in which we are working for our chain pitch. So to do that, I'm going to head down to table 2 over here. And the first thing that I see on the x-axis is that I need to select the RPM of the faster shaft. So we now know that it is 80 RPM. This was given in the question. So I can perhaps just follow this line up over here. And then the design power we calculated is 1.8 kilowatts. So it's probably going to sit somewhere over here. And then I simply have to go and look at where the intersection of those 2 lines are, which seems to be around here somewhere. Okay, so, and that means I'm then working in this blue streak or this blue region that I have over here. In other words, the chain pitch that I'm going to select is the 16B 1 inch 25.4 millimeter chain. Okay, so I just write that down over here as well. And then I can move on to calculating the speed ratio. So remember that the speed ratio will always be the faster shaft RPM divided by the slower shaft RPM. So in our case, we're working with 80 RPM and 40 RPM. So it's simply 80 divided by 40, which is then going to give you this 2 over here. Right, so then I just need to head over to my table. I'm just going to delete this for now. So to select then my sprocket sizes. So this is given in table 4 on page 6. So if I head down to page 6 over here, so you'll see there are a few cases where I have a speed ratio which are not in bold, but it's still 2. In my case, since I don't have any space constraints, I would rather want to select a ratio which is in bold. So if I look over here, I can see that the 2 speed ratio that I calculated over here is given in bold. So that means that one of my sprocket is going to have 19 teeth and the other sprocket is going to have 38 teeth. Just something to note as well, with regards to these axes labels that I have over here, both of them actually say number of teeth driving sprocket. And this one also says number of teeth driving sprocket. So you will have to go and determine on your own which one is the driving sprocket, which one is the driven sprocket teeth. Okay, so to do that, what we can go and use is the ratios or the gear ratios that we have available. So to illustrate that, what we can say is if I have omega 2 over omega 1, so the RPM of shaft 2 divided by the RPM of shaft 1, then this will be set equal to N1 over N2. Okay, and this is a standard equation that we have available. So when we compare the RPM ratio with the number of teeth ratio, we have to switch the numbers around. Okay, so if I'm working with RPM on shaft 2 at the top, then it means its number of teeth will be at the bottom. And then if I'm working with RPM of shaft 1 at the bottom, then it means that its number of teeth will be at the top. Okay, so in our case, we said that we have, I think, 80 RPM on our driver shaft, and then 40 RPM on our driven shaft. So to make sure that I get the same ratio, I then have to take the number of teeth that I got from the sprocket sizes table, so that will be 38 divided by 19. So since I'm working with the RPM of the driver shaft at the top, its number of teeth will be given at the bottom, and the RPM of the driven shaft means that its sprocket size will be given at the top over here. So 38 teeth on the driven sprocket and 19 teeth on the driver sprocket. Okay, so that's just with regards to how we will go and determine that. Then there's just a few points that we can also look at over here for any general recommendations on these sprocket sizes. So this is also given at the bottom. I think it's actually given a bit earlier. So this is on page 4, where we actually have the table where we select the chain pitch. And you'll see for 19 teeth and above, these are used for sprockets running at medium to maximum speeds on normal applications. Alright, so then for step F, we're just going to calculate the power rating, and for that we're going to our power rating tables on page 5. So these tables are set up in terms of the chain pitch, so you'll have to go back to step C to check what chain pitch you used and then go to the correct table. Once you have the correct table, you're simply going to the RPM of the faster shaft, and you're going to read off whatever the value is for the simplex power rating. So we start off with the simplex. If the simplex power rating is higher than the design power, then it's fine. Otherwise, we can go over and select the duplex if we want to. Right, so in our case, we're working with the 16B chain pitch. Our RPM of the faster shaft is 80. So in other words, for a simplex chain, our power rating is 3.79 kilowatts, which is indeed larger than the design power. So you'll remember we calculated that as 1.8 kilowatt. So since it is larger, a simplex chain will actually solve the problem that we have. Okay, and this we can see over here as well, a small sanity check that we made. Right, so then it's just a matter of calculating the chain length. So for the chain length, we now have the number of teeth on the large and the small sprocket. We just need to go and determine the recommended center distance, the chain pitch in millimeters, as well as this K factor that we have over here. So the K factor, to perhaps start off with, is found in table 3 or page 6. So if I head down to page 6, you'll see it's above the speed ratios table over here. And we need to take capital T minus small letter t. So in our case, the largest sprocket has 38 teeth, the smallest sprocket has 19 teeth. So 38 minus 19 is then this 19 over here. And if I read to the right, I can see that the K factor will then be 9. Alright, and then I also need to go and determine the recommended center distances, and then the chain pitch as well. So this you'll actually find on page 3. So I now know that my chain pitch is 1 inch. I got this from the graph. So then the chain pitch in millimeters, just to double check, is indeed 25.4 millimeters, the same as what it was on the graph. And then the recommended center distance is then 1000 millimeters. Right, so now I have everything available to actually go and calculate the length of the chain in pitches. So I'm just going to head over to an Excel spreadsheet. I'm going to create a new blank workbook. And then we can simply create the question over here, because we want to use goal-seek once we've performed the initial calculation to recalculate our actual center distance that we have. Okay, so just to make it a bit easier, I'm just going to take the equation over here and copy it over. All right, and then I can start populating the data cells. So I'm first going to say C, which is the recommended center distance, is 1000 millimeters. Then P is the pitch of the chain in millimeters. We found that to be 25.4 millimeters. Then we have the number of teeth on the large sprocket, which is 38. And then the number of teeth on the smaller sprocket is 19. Addition to that, we also have the K factor, which is simply 9, and it is unitless. Right, so to calculate L, that is simply going to be equal to 2 times C divided by the chain pitch in millimeters, plus, then I'm just going to place in brackets large sprocket teeth plus small sprocket teeth divided by 2, plus, and then it's K times P, so K times P divided by C. And then I can hit enter. Okay, and this value is then in pitches. Right, so now you'll notice the value that I got is 107.469, so it's not a rounded value. And from the slides, we said that we like to round off our chain pitch, or the length of the chain, to an even whole number. So I'm just going to do that, and we always want to round up. So I'm just going to say L rounded is then equal to round up whatever this value is to 0 decimal digits. Okay, so the actual number of pitches, or the chain length that we're looking for, is 108 pitches. Right, so to achieve this, what I can actually do to make sure that the calculated L value matches the L rounded value is to go and adjust my center distance. And I can do this because I don't have any space constraints that I currently have to consider. So to do that, I'm first going to calculate the difference between the rounded and the original value. So that's 108 minus 107.469. And now I can go and use something like the goal-seek function to make this difference 0. So if this difference is 0, it means that this value will be 108. Okay, so alternatively, what I can also do is I can simply do a goal-seek on this L value over here as well. So let's perhaps do that. So I'm just going to say what if analysis, goal-seek. And then I can select this value over here. And I want to set it equal to 108 by changing the center distance cell over here. Right, and now I can see it did find a solution. So in this case, the goal seeking with cell E20 found a solution. The target value is 108. And the current value that it calculated is very close to 108. We can actually see this from the difference as well, which is 5 times 10 to the power of minus 6. Okay, so if we just check our center distance, our actual center distance is, in this case, is then 1006.8 millimeters. Right, so that is then the actual value. So it differs slightly from the recommended center distance. Okay, so just going back to the slides, we can just double check that, and we can see that indeed we then have 108 pitches, 1006.8 millimeters. So if we want to go and calculate our chain length in millimeters, we can simply take the 108 pitches and also multiply that by 25.4, which is the chain pitch in millimeters. And then we should get this 2743.2 millimeters over there. Okay, so just before we move forward, with regards to some background with the chain offset link that we can use. So offset links are used to add a half link to a strand of roller chain. Any strand of roller chain without the use of an offset will only have an even number of links. So if your chain is a half a link too short, then you will require the use of an offset link. Now these links are primarily used on drives that have shorter lengths of chains, where tensioners or adjusters are not used. So of course there is a disadvantage of using these offset chain links, being the fact that it then induces a weakest link in this chain that you set up. So drives with low speeds and low loads may not necessarily be impacted with the use of an offset link. However, if it is possible, we want to design the application so that it does not require the use of an offset link. Okay, so that's why we also adjust the center distances if it's possible without any space constraints. Okay, so then just moving one forward, we now need to actually go and define our drive specification. So to do that, we need to get some information regarding the bush number and the designation. And to do this, we go to page 22 of our Fenner catalogues. So if I just type in over here 22, you'll see you have these taper lock sprocket tables over here. So these tables are once again organized in terms of the chain pitch. So in our case, since we're working with a 16B, I'm just going to scroll down to the second table that I have over here. And now to go and define the actual drive, I'm just going to start off with the number of teeth. So we know on the driver sprocket now that it has 19 teeth. So I'm just going to follow this over to the simplex taper lock since we're working with a simplex chain. And I want to read off the designation and the bush number. So that is 81-19 for the designation. And the bush number is 2517. And then for my driven sprocket, I know I'm working with 38 teeth. So in other words, the designation for that would be 8138 and the bush number would be 3020. Okay, so now I have that information available. Just something that I also want to point out, I think it was on page 2 or 3 where we looked at the actual example. So the example that we did in the slides is simply copied over from the catalogs over here. We also just mentioned that the gearbox output shaft is 35 millimeters and the conveyor head shaft is 65 millimeters. So this design data was also given to us. So now if we want to go and define the drive specification, what we're going to do, we're first going to give the chain length in pitches, and then we're going to say, so it's 108 pitches of Fenner 16B-1. So 16B is the designation that we use for the chain pitch, and then -1 because we're working with a simplex chain. So if we were working with a duplex chain, that would have been -2. Otherwise, for a triplex chain, it would be -3. So once we've defined that, we simply have to go and define our driver and driven sprockets as well. So we start off with the designation. So in the case of the driver sprocket, it was an 81-19 driver sprocket with a bush number 2517 by 35 millimeter bore. And then for the driven sprocket, it was 81-38 driven sprocket with a 3020 by 65 millimeter bore. All right. And then finally, if we just want to determine the product codes that we would need to actually order these parts, what we can go and do is head over to the shaft fixings catalog. So you'll see here at the top, I've also referenced it. So if we head over to that, you'll see on page 8, these metric bores and keyways table starts, and this is then the taper lock metric bushes that we're looking for. So since we have the bore diameters and the shaft diameters available, we can actually just go and trace that horizontally. And we also then have the bush number available. So in the case of the 35 millimeter driver sprocket with the 2517 bush number, we're going to need a product or a taper lock metric bush with product code 029 M0035. Is what we're going to need for that one. And then for the 65 millimeter bore, which is then on our driven sprocket, we use the 3020 bush number over there. So the product code corresponding to that would be 029 P0065. Okay, so once we have that available, we've then fully defined our drive specification. Just the last point that I then like to make as well is you'll see we also have installation manuals available. So if I head to the Fenner chain installation maintenance manual, you will see at the bottom of, I think this is page 2, you'll see depending on the bush size that you're going to select, you also have a few different other selection quantities. So the screw tightening torque that you will need, the number of these bushes, and then any screw details as well, and then some additional properties as well. So we can always ask you for the bushes that you've selected, what is perhaps the screw tightening torque that you would need. So since for our driver sprocket it was 2517, then the tightening torque would be 50 Newton meters. And we would need a quantity of 2. And then for the screw details, if we use a hex socket size over here, the size would be a 6 millimeter. Okay, and then we have some additional information over here as well. Alright, so that then sums up the example that we did where we don't have any space constraints. So in the next lecture, we will move on to example 2, where we then consider certain space constraints and how that will affect our design process.